Yes, so it's a pleasure to have the speaker today is Elisenda Feliu. She is associate professor at the University of Copenhagen. She started in very traditional, good algebraic geometry, intersection theory, my understanding was your dissertation in, and arithmetic K-theory. And for some time, she is applying all the good algebra to biological problems. And so it's a pleasure. And I should also mention, of course, that she is associate editor of the most important journal, SIAGA, and is doing a very good job there. So it's a pleasure to have you as a speaker, and I'm looking forward to your talk.
Thank you, Joachim, and thank you, the organizers, for inviting me here. Thank you, everyone that joined the seminar today. And yes, I started in very, very pure math. There is no example in my thesis. That is very different now. There are a lot of examples I work with and a lot of concrete scenarios I look into. So this talk is about parametric polynomial systems that arise when I study biochemical reaction networks, but the focus today will be more on the polynomial systems and not so much on how we build the systems and where do they come from and so on. Many of you maybe already have heard talks about reaction networks in this setting, and therefore that part will be a bit brief today. So what is the overall goal? Our goal is to study polynomial systems that have this form. So they have like n variables, so here 4, and there are two types of equations. On one hand, we have some equations where the coefficients are parameters, and the parameters are assumed to be positive. And therefore, you can think of this part as we have a fixed support. We have fixed the support of my polynomial system. I have fixed the sign of the coefficient, and then I vary the coefficient. And on top of that, in some cases, I've also decided that two of the monomials that are the same will have the same coefficient exactly, right? You see K2 here and K2. So this part is just a family of polynomial systems, and I would like to understand this family when x is positive. That's because x are concentrations in the application setting. So that's the first part, and then we intersect or we complement these equations with some linear equations where now the parameters are just given by what is the level set I'm considering. Geometrically, I think it's more clear the picture. We have two families of algebraic varieties given by the zero sets of these equations, and then the red here drawn corresponds to the first part. This drawing is in 2 dimensions, so it's not the same system as here, it's just for illustration. So we have a family of red curves, and then we have a family of linear subspaces. And what we want to understand is where they intersect, right? So every time I pick a red curve and a blue line, how many intersection points there are, for example. Here you can see in this figure, if you pick one red and one blue line, there is always one point where they meet only. While in this figure, if you pick lines here, you will see there is one intersection point for this line, like whatever blue line I pick, there is one point intersecting. But for this red line here, if I pick this line here, then there are 3 intersection points, right? So for this figure, there is also always one solution of this equivalent system. And for this figure, the number of solutions depends on the parameters I choose, right? The set of solutions, I call it C, and in subindices, I denote the parameters I'm using. And I emphasize again that I'm looking at the positive solutions only. So for today, what I will be mainly talking about is the property of when, how, and why this set will have at least 2 points, right? And the questions, the specific questions of interest are whether I can find parameter values for which this set has at least 2 points. This is a property called multistationarity, and the name comes from the application setting. If that's true, where does it happen? How can I determine the parameter values for which this happened? And then, even if I can find the parameter set where that happens, how does it look like? What is the shape? What are the properties this set has, right? And for today, this property will be connectivity, whether it's connected or not. So this is the overall setting and the overall topic of this talk. And well, to answer these questions, there are algorithms from semi-algebra geometry that in theory can answer these questions, but in practice, the systems I'm interested in are too large for these methods to work. And therefore, what we do is to find other routes to answer the questions in different ways. And that's what the talk is about today. So what's coming now is 2 slides on the origin of the system, such that you know where it comes from and you know why it's important. But as I said, not much emphasis will be put on that. And then there are 3 parts of lead independent questions. The first one is to understand the parameter region. And to this end, I will also talk about a joint work where we studied importance system in cell signaling. The second part, which shorter, I will talk about the connectivity of this parameter region. And the third part, if there is time, I'm not that sure about that, will be how can I approximate the region instead of finding it exactly, how can I find a numerical approximation of the region. So let's start with the first part about the origin of the system. And the system comes from some reaction networks. A reaction network, you know, it's a collection of reactions, chemical reactions. And as mathematicians, we just put the species or what reacts X's, right? X1, X2 are my 2 species. And then this is how they relate. This is how they interact. When you have that, you can associate to each reaction a positive number. These are the kappas that appeared in the first slide today. And then one way to study the evolution of the concentration of this species in time under some hypothesis is via a dynamical system, a system of ordinary differential equations, which is built as follows. You consider the net production of each species in each reaction. Here you see each column has a color. It corresponds to each of the reactions. The first column encodes how many X1s are produced. Well, -1, because there is only one X1 that is consumed. That's the -1 here. And how many X2 are produced? Well, there is 1. Every time the reaction takes place, I gain 1 X2. And that's the 1 here. For example, for the last reaction, when the reaction takes place, again, I lose 1 X1, that's a -1 here, and I use 1 X1, but I gain 2. So then 1 is gained, right? So that's just a simple combinatorics game to see how many new molecules I get and how many I lose. And then the next part is to decide how fast that happens. How often does the reaction take place? And this is where some assumptions need to be made. And for the talk today, I will, for the application, I consider what's called the mass action kinetics, which just says that the rate at which a reaction takes place is proportional. That's the case I have here, to the product of the concentration of the species in the reactant, right? So here I only have X1, that's why you get K1, X1. Here I have K1, K2X2, then I would have X2 squared, and then the proportionality constant. So that's the first ingredient, and this system can always be built for whatever network you draw. You can find this matrix, which is called the Stoichiometric Matrix. You can find this vector of monomials from the reactants, and then you put a reaction rate constant, a parameter in front, right? And these parameters are positive. The second ingredient is that you can see that whenever this matrix doesn't have full rank, that there are linear relations among the rows, they give a linear relation among the derivatives, right? So if I have a matrix such that Wn is 0, then Wx dot is 0. And that means that the trajectories are constrained in these spaces of the form Wx equals c, right? So the system is not n-dimensional, it's actually, in fact, it has a lower dimension. So this part is the part that was the upper part in my opening slide. And this part are the linear equations I showed you. When we set this to 0, we are finding the equilibrium points or steady states of the dynamical system. And in dynamical systems, if you want to study the system, you start by finding the equilibrium points. It's like the first step mathematically. So the intersection of the set of points where this is 0 with these linear invariant spaces gives me the equilibrium points in these spaces where the trajectories take place. So that's where this system comes from. My C kappa C has this form. And in the example I had, it would be this system, right? But because every time I have an equation like this, it's because I have a linear combination, a zero linear combination of the equations coming from the steady states. It means I can get rid of one equation, right? So for each equation in Wx equals c, I can get rid of one equation here. And in the end, I end up with a square system in the sense that I have as many equations as variables. Yeah. And then we expect that these sets will have a number, will contain only points, so it's a finite number of points, but the number will depend on the parameter values. And deciding when there are 2 points or more, it's a question that comes from biochemistry, because each of these points, each of these solutions is a steady state. And that is used, or it's believed that it can encode the different states a cell can be in. And it allows the cell to be in 2 different states depending on where it started. That's the motivation part, right? But now I will stop talking about somehow the biochemical reaction networks. They will appear as examples, but now we focus on the mathematical questions, right? How can I decide when my C kappa C has 2 points at least? Well, that's an interesting question, but even when we can answer it, which doesn't happen often, we get complicated answers. Like this is a network that bacteria use to transfer a signal. And here one is lucky, one can decide that the network has 3 positive steady states, even only if these relations occur. And each of these A's is a polynomial in my parameters, right? Okay, one can be happy, one has an answer, but one doesn't know what to do with the answer. There is no clear interpretation, biological interpretation of these relations. It's not clear how to study the region, how to determine the properties it has. And that's the common problem here, that even when we can find the region, we cannot use it that much to study. So
there's
yes.
a question in the chat.
Yes.
Maybe it's related to the previous slide, but does this mean there are constraints on what linear equations can be given your polynomials? For example, it seems like the linear equations are determined by the polynomial equations via some matrix of coefficients. Is this right? Or?
Yeah, the linear equations arise from this n, right? So the W is a matrix such that W times n is 0. But once I get rid of the redundant equations, like here, this one arises because this plus this is 0. So I have x1 plus x2 constant. But once I get rid of the redundant equations, then there is no relation. I cannot find this equation from this. So in the original system, I had the square system with as many equations as variables. The 2 sets are independent. You don't have connection. I hope that answers the question.
Thank you.
Yes, so as I was saying, it was difficult to understand these full parameter regions and also to find them. And that led a bit to find projections of the parameter region. So instead of finding the whole parameter region, can I project it into some set of parameters and get more information out of it and maybe a biological interpretation. And in that direction, I'm aware of 3 works. One is where to understand the parameter region where you project to the kappas, sorry. One where one projects to subset of the kappas and the Cs, and one where one understands the region only on the Cs. And the first one is the one I will be talking about now. And to this end, I introduce a nomenclature to say that I say kappa enables multistationarity if I can find a C such that this holds. That is, kappa is in the projection of the parameter region of multistationarity to the kappas. And therefore, the new question is, how can I find the kappas that enable multistationarity? Here in the drawing I started with, the kappa giving this red curve enables multistationarity because I can find a blue line that gives me 3 intersection points, and the kappa giving rise to this red line does not enable multistationarity because I cannot find the C that enables multistationarity. So this, to this end, I will talk about what's now maybe an old theorem. It's from 2017, but it took time to publish the paper, so we had it already in 2015, I think. And it's as follows. It says, consider a network, and then there are some technical conditions I want to skip. If they hold, then, and I fix the kappa, I can find a polynomial with the following property. If that polynomial is positive whenever I evaluate it at a positive x, then my set C kappa C will have one element for any C, right? Kappa is fixed. If that's not true, if I can find an x such that the polynomial is negative at a positive value of x, then I'm guaranteed that I will be able to find a C such that this set has at least 2 elements. That is, this kappa enables multistationarity. This mysterious polynomial is nothing else than the determinant of the Jacobian of the system I showed you in the beginning today, evaluated at a steady state. That's a part that not always can be done. And this follows from degree theory. It's just that we compute the Brouwer degree to be -1 to a number. So we can compute it, and that's from where this is derived. But let's see how this works in practice, right? Let's start with the network I showed you before, where the answer was complicated. Here, the polynomial is this one. It is in the variables x4 and x5, and you can see the coefficients depend on the kappas. Yeah? And now we need to understand when this polynomial is always positive over the positive ortho, or when it can attain negative values. So first observe all coefficients are positive except this one, right? So if this coefficient is also positive, there is no way I can make this polynomial negative, right? So if this is positive, equivalently, if this holds, then the polynomial is positive. I go up here, there is 1 point in my set for any C. What happens if the coefficient is negative? Well, that requires some more work, but this polynomial, you can see this monomial that goes with a negative coefficient is of degree 3, and the rest of the monomials have degree lower than 3, right? So then if you just say x4 equals x5 equals some t, you evaluate it, you get a degree 3 polynomial with negative leading term. If you let t be large enough, the polynomial attains negative values. So this polynomial will attain negative values, therefore I have that this set will have at least 2 elements for some C. Okay? If we put it all together, K enables multistationarity, even only if K1 is smaller than K3. Right? Going back to here, I don't see that K1 is smaller than K3, obviously, that it's the projection of this set, right? But we got it quite easily from this theorem. And also, this is an inequality that has a biological meaning. If you go back to the reaction, of course, you don't know all these symbols, what they are, but you can see that here, this is a protein that has, there are two places where a phosphate group can be attached, and the P indicates the protein with a phosphate group in the site. So here you see K1 regulates how fast a phosphate group gets attached in the first site when the other site is free, and K3 is the rate at which the phosphate group gets attached in the first site when the second site also has a phosphate group, right? So this is just saying, to get multistationarity, I need that the second site having a phosphate group is an advantage, makes the reaction go faster, right? And of course, the biology is like, I mean, it's an interpretation of why that happens, and therefore this condition is important for them. So that's this old work. So what have we done? We have gone from the original problem, which was understand for which kappas and Cs that system has at least two positive solutions, to another problem that is understand for which kappas my polynomial will attain negative values in the positive order, right? If we think in semi-algebraic terms, maybe we haven't gained that much, because deciding this question is also computationally hard. But the thing is that to answer this question, we can use techniques from polyhedral geometry that work quite well. And that's what I will focus on for the rest of the talk almost. So here is the question. I mean, in the example I gave you, I said, when this coefficient is negative, then my polynomial also attains negative values. And of course, I was lucky to be able to do that, because that's not true that just because a polynomial has a negative coefficient, the polynomial might not attain negative values. And the canonical example is this polynomial that is always non-negative. So, but then there is a result that one can use that relies on the Newton polytope of my polynomial. And that's as follows. If I have a polynomial, the Newton polytope is built by considering all the exponents and then taking the convex hull of the exponents. So in the polynomial I had before, my monomials here, for example, this is x4, the exponent vector is 1, 0, is this point, right? For this one, the exponent vector is 1, 2, it's this point. So I do that for all the points. I have 6 points because I had 6 monomials. I take the convex hull. And this region here, this object here is the Newton polytope. And then when we have that, there is the following proposition that Timo de Wolf told me that's folklore in real algebraic geometry. So I assume many of you here know, but not everyone. So this is, it says the following. If you have a face of the Newton polytope, say, for example, this one, right? And you restrict the polynomial to the face, that means I only keep the monomials that lie on the face, that would be these two, right? If that smaller polynomial is negative for some x, then I also know that my original polynomial can be negative. And if my smaller polynomial is positive for some x, then my original polynomial is also positive. That is, all the signs that can be attained by a face are also attained by the whole polynomial. And that, if we think of a vertex, the vertex is a constant, essentially, or the sign is constant. This result says that the sign of the coefficient of a vertex can be attained by the polynomial evaluating at positive numbers. And that's what happened here, right? My monomial here that I had before corresponds to a vertex, and that's why I could do that trick to say then the polynomial is negative, right? So using this, so computing the polynomial and looking at the vertices of the Newton polytope, we can get inequalities in the case, like imposing coefficients to be negative, that will ensure multistationarity, right? In a quite almost automatic way. But it's not always that the story is so easy. And this is for this system, which is called the dual phosphorylation cycle. Here the polynomial is a bit larger. It looks like this. And you can see I marked in blue the coefficients that can be negative. The ones that are not blue cannot be negative. And you can see that essentially there are two expressions that control the sign of the coefficients of this polynomial. There is this one that appears several times, and then there is this one that appears only one time. Right? Then we try to do the same as we did before. We say, okay, if both coefficients are non-negative, right, then the polynomial cannot be negative. Then I have one point in my set for all C. Then it happens that this one corresponds to some vertex. Then we are happy. We are in the case that is easy. So it means that if this coefficient is negative, then I guarantee that I can find X such that the whole polynomial is negative. And therefore, there are 2 points in my set, right? These two conditions were found by Conrad and Mincheva in 2015. But then the question or the problem is what with P2? I mean, P2 is not a vertex of the Newton polytope. It's this point here, this blue point lying on this hexagonal face, right? And now here, it's not enough to look at the exponent, right? You can see here, these two polynomials have the same support, but this one cannot be negative, but this one can be negative. So how large the coefficient of the negative point is with respect to the rest is what determines whether my polynomial can be negative or not. So I cannot answer anything by just looking at the exponent. So here, that was the question, and I posed the question to Timo, I think already in 15. And then we kept meeting in conferences. Yeah, we have to look at that. We were saying, we even sent the polynomial, I think in 2017 to him. And it was not until, I think later on in 18 or 19 that finally we started talking with also Nidika Insa and Augusta in Europe. And then we found a bit an answer of what's happening with this point here. And it relies on the circuit numbers that Timo has worked with a lot. And the idea is very simple somehow. We consider polynomials that are supported in a simplex, like here, and have an extra point, which is in the interior of a simplex, right? And we assume the coefficients of the points, the vertices of the simplex are positive, and we assume that the point in the interior corresponds to a negative coefficient. Right? Then the theorem you can find here says, okay, write the point in the middle in convex coordinates. You can always do that because it's a simplex. So for example, this point has this, you can write it in this way. Then when you have done that, these are your coefficients. Then if beta, the coefficient of the point in the interior, is at most this quantity, which depends on these coordinates and the exponents, the coefficients corresponding to the vertices. If that holds, then your polynomial is non-negative, right? So in this example, the condition is that beta has to be smaller than 3 times this expression. Can we use that? That was the question we had, right? Can we use that? And well, we don't have a simplex here, right? But the first thing we can do is, because the vertex is on a face, we can restrict the polynomial to the face, because as I said before, the signs that the polynomial attains on the face are enough. And the face is a hexagon, and there are actually some extra points, 2 on the edges and 2 interior points. And then it happens that our blue point is the barycenter of 4 different simplices. These 2 triangles here, and these 2 segments here. Right? So what we can do is split the coefficient of my point such that I write my polynomial as the sum of 4 polynomials supported in a circuit like I explained before. Then we apply the conditions for each of the pieces and we put it all together to say that if that coefficient is not larger than this, then my polynomial is non-negative and therefore I only have one solution. Then with a bit more work, we could also study what happens when there is more points, but the coefficient is negative, right? And again, we used a lot the tricks with the Newton polytones, that maybe now Newton polytones involving the parameters, playing a bit with these tricks. And we could see that if 2 of the parameters are large enough, then, and P2 is negative, then we can have that this set has 2 points. Therefore, as I said, knowing the sign of this is not enough. Both scenarios occur. We also could find an explicit parametrization of the boundary where the region where the case-enabled multistationarity and not occurs. And then also exploring the Newton polytope, we could see that the 2 regions are connected in the kappas, and that the multistationarity region is an open set, and the monostationarity region is a closed set. So here it was like the first somehow result concerning connectivity of the parameter region, but that's not the parameter region, right? That's the projection of the parameter region of multistationarity on the kappas. So that leads to what happens with the parameter region on the kappas and the C. Can I study the number of connected components, or how can I do that? And that's a question I have posed to several people. I think back to 15 again. I didn't know how to answer this question, and I wanted to answer this question because, as I said, mathematically, you are interested in a region. The first basic property maybe is to understand, is it connected, right, by region? But also biologically, these points, these parameters tell me that the system has the capacity of a property of interest. So if I know there are 2 different connected components, then I know there are maybe 2 mechanisms giving rise to that property. If the region is connected, then there is a continuum between any 2 parameter points that gives me that property. There is a continuous way to go from one to the other. So they do not represent 2 different mechanisms somehow. So if the region is connected, then I can say, okay, then the reason is somehow the same for all the parameter points. That's a bit hand waving, right? But that's a bit of philosophy of why I would like to know that. And well, as I said, I posed the question to several people. The only paper I'm aware of where they studied this for reaction networks is a very recent paper that I know. It wasn't, the research was not that recent, but maybe it took time to wrap up the results, where you can see here there is Dan Bates. They use some tools from homotopy continuation, numerical algebra geometry to study whether the parameter region for that dual phosphorylation cycle I showed you before is connected or not. And they conclude that it seems that it is connected, right? So that's the only result I'm aware. And well, very recently, Mate Telek came to visit my group as a research assistant in October. And as I do with many people, I gave him this question: how can I decide whether a parameter region of multistationarity is connected? And I gave him the histidine kinase, that it's HK example I showed you before. And well, he made a great realization, which is the following. Remember the polynomial, the p kappa x I had before, right? But now I look at it as a polynomial in kappas and x, not only a polynomial in x. Though in the example there was a K3 dividing, you can see you can just multiply by K3, right? Then he realized that there is a one-to-one correspondence between the connected components of the parameter region of multistationarity and the connected components of the following set, the set of kappas and x, positive, that make the polynomial negative. And this is based on that theorem I showed you before. So here I show you a polynomial. So what we are after is to understand like the complement of the hypersurface given by the polynomial. So that's the hypersurface. Then the sign of the polynomial is constant in each connected component. So we want to count in how many of these connected components my polynomial is negative. Okay. So that was the first important observation. But then, of course, we had to decide that, right? How do I decide the number of connected components where a polynomial is negative? And again, the Newton polytope is very useful. I mean, we have several results to decide that, but I show you one today, which again follows simple arguments relating signs and polynomials. And it says the following: assume that X is a separating hyperplane in the space of parameters, so the variables of the polynomial, such that on one side, I only have coefficients that are positive, or I only have points that correspond to coefficients that are positive, and on the other side, I only have points that correspond to coefficients that are negative. And this is the picture. This Newton polytope corresponds to this polynomial. I need to remember the points. It's not enough to take the convex half. So I need to remember the points that are exponents. And then the empty dots have negative coefficient. The solid dots have positive coefficient. And you can see this red line here separates that on one side I have positive points, and on the other side I have negative points. And it doesn't matter what happens on the hyperplane. It doesn't matter. I have both signs. It's okay. If that's true, and if there is something in both sides, so there are positive and negative points at each side of the hyperplane, then the parameter region of multistationarity is connected. That is, this set has only one connected component. With that, we could conclude that this system, the multistationarity region of this system is connected. And you can see why, right? I have only one negative point. I can just draw any hyperplane here. It will separate the two signs. Therefore, I can apply the theorem. And now remember, for this system, I had the region explicitly. And from these equations, it would have been much more work to decide that this region was connected, right? Because that's the region I'm studying. Then the same happens for the dual phosphorylation cycle. I mentioned that numerical work where they show that that it hinted at the region being connected. Now we can confirm that it is indeed connected, and this is a higher dimensional object. It has 11 variables, but still one can find this hyperplane separating. So that would be for connectivity. And I think I will briefly say something about the last part, because there are many algorithms to decide in the field of reaction networks whether there exists a point where this set has at least two elements, just the existence question. But these algorithms, they give you a point that they find through the algorithm, but you cannot tell them, find me a point in this box. And that's what biologists usually want. I mean, they know, these parameters have a physical meaning. So a kappa cannot be 10 to the 8, for example, right? So they know the ranges where these parameters live in. And you want to decide whether there is multistationarity in that box they have, right? So that was the question we wanted to answer here. This is with Amir Sadehi-Manesh. And for this work, we've tried a numerical algorithm. And the theorem that it builds on is a bit technical, right? So I don't expect that you can process all this now at the very last 2 minutes of the talk. But let me briefly say the idea, right? The idea is that we consider a parametric polynomial map, as we had before. We have some parameters, and we think these parameters are equipped with a distribution, like the uniform distribution. Right? And then what I'm interested in is on finding the average number of positive solutions of this polynomial when these kappas follow this distribution, that is the expected value of that in the box. And for the theorem to work, I would like my polynomials to have a nice form, to be linear in one parameter. So each polynomial has to be linear in one parameter, and that parameter can only appear in that equation. And that seems a strong condition, but that happens for reaction networks. And then we define some objects. We isolate the kappa from this. So we transform this equation into this. And then we evaluate the densities of the distribution into the value we obtain after isolating the kappas. And then we get this formula that the expected number of solutions my polynomial system has when I restrict it to a box. So here for us, this will be the positive ortho, can be computed through this integral where that involves a determinant of the Jacobian of G and the densities here. Well, as I said, the conditions hold for reaction networks, so we can always apply this. And of course, computing this integral is not something you can just do analytically, but we have used Monte Carlo integration, which involves sampling a lot of points. And when you need to sample a lot of points, and you can do it in parallel ways. So we could compute this integral with Monte Carlo integration and parallelization. And what can you do with that? Well, you can find grid approximations of your parameter region. This is a simple example with only 2 parameters. This is the real region of multistationarity found using cylindrical algebraic decomposition. And then this is what we can do. You can decompose your space into squares, find in that square the average number of solutions. And then if the average number of solution is 3, you know you are inside the region. And at the boundary, I mean, your boundary goes here, right? So you will have an average number, which is between 1 and 3. And this can be done, then you can go and refine the boundary if you want to get a better approximation of it. So that's one thing one can do. And the second thing one can do is what I said before. Let's imagine I'm given this box and I want to know, does it contain any point where, or any subbox where all points have multistationarity. And you can do that by bisecting, like you compute this average number for this and for this, and then you see that for this one it's higher. So you take this one, then you divide. For this one here it's 1, then you pick the other one, then you divide, and you keep dividing by picking the highest average number until you find an average number that's close to 3. Of course, all this is numeric, so we need to take into account the standard error and all this. And these are examples with 2 variables, but we were able also to kind of find regions of multistationarity for the dual phosphorylation cycle with 15 parameters and 3 variables, for example. And here we used heavily that we had some servers with 32 workers. So in 16 hours, we could go from this box to a small box that is entirely inside the region of multistationarity. So to wrap up, so this talk was about parameterized polynomial systems and to decide, to answer questions about when and where do they have at least 2 positive solutions. The study of polyhedral objects have been proven quite useful in this setting, and also some numerical new approaches that's called Kac-Rice integral can be used. And I will conclude with a small advertising of this part, because there are all these nice conferences coming where some of the things I've said will be expanded. So in the SIAM conference in August, Telek will talk about connectivity, Insa about dual phosphorylation cycle, and the Wolf more about circuit numbers and multistationarity. And in Mega, which is next month, Yuruk will also talk on circuit numbers and multistationarity, but for an extended system. That's some SQL work we are doing, extending what we had for the dual phosphorylation cycle to the end site, what's called phosphorylation cycle. So that was it. I will thank you for your attention.
Many thanks, Elisenda. Are there any questions from the audience? And there are some questions here in the question and answers. Is the sign, this was actually a question a little earlier already from Austin Alderete. Is the sign equal plus case related to the global attractor conjecture?
No, it's not. It's not related.
Okay.
No, because it will just say there is one solution, but it doesn't say anything. Well, you will know the sign of the determinant, but you don't know the global.
Okay. So there is no direct additional question. Jose, do you have anything? Or
so
otherwise, what we are doing here is anybody who wants now to join the coffee break, gets promoted to the panelist thing, and we can ask questions then informally, or just take away with the transparencies and have in gallery view everybody who is present and can exchange a little bit thoughts about the talk and beyond. So, but I thank you again first from my side. It was really interesting how this algebraic techniques play a role in a very nice set of applications.
Thanks.
Good. So, Jose, you can promote people who want to come to the room, and how does it work?
Yes, just use the raise hand feature and I can promote people.